Hello, everyone. I am Sufyan Al-Janabi from University of Anbar, Iraq. I'll talk about supporting the unconditional secure authentication services within internet security infrastructure. I'll try with starting with some talk about the problem statement and the objective of the work. Then I go fastly through some aspects of the proposal before concluding the presentation. As you know, there are big security challenges for different internet services and applications now. And I think it's time to try to switch to some evolutionary security solutions. As you know, almost all security solutions on the internet are based on cryptographic structures that are only computationally secure. What we mean by computational security, that they are secure based on our estimation of adversary power, processing power, and mathematical knowledge. So possibly it's time to start to work with structures, mathematical structure or cryptographic structure that are that can achieve the strongest definition of security, which is unconditional security. In that case, we can be sure that this algorithm or this protocol cannot be cracked anyway, regardless of the processing power of adversary, and we can reduce the probability of a crack to a significantly very, very low number. Considering authentication, which is a basic security service for any application, we have mainly three constructions. The first is the message authentication codes, which are almost being used for all applications considering authentication. However, they are only computationally secure. While what we are proposing now is to start using authentication codes, or what we call A codes. These are different mathematical structures that can achieve unconditional security, not only computational security. And of course, digital signatures can be derived from MACs or A codes. There is no problem in that. But the issue now is we want to achieve unconditional security, not only computational security. And I'm talking about authentication as a generic term. I'm not proposing that we should forget about MACs and use A codes. No, I'm proposing to use A codes besides MACs. Because MACs, because they can only achieve computational security, are not suitable for applications that require long-term security, say for 20 or 30 years. Especially we are witnessing a technology breakthrough now of quantum computers. And we have a number of quantum computers around the world. And I think it's a matter of maybe 10 years before we see some commercially available computers. And in that time, many computationally secure construction that we are considered to be secure now, like the RSA and other construction based on discrete logarithms or factorizations of large integer will not be secure no more. And we already in cryptography, we have a new emerging paradigm of post-quantum cryptography, the cryptography after the appearing of quantum computers. So while we are, my talk is not really only related to e-government, because it can be considered for any security-related application on the internet. But I'm focusing on e-government because I think it is one of the first areas that can benefit from this proposal. Actually, we need to re-engineer some parts of the infrastructure, and we have to add some additional functionality and some modification regarding software and hardware. Among these functionalities is the issue of key synchronization. One of the most challenging issues regarding the deployment of unconditional secure authentication services are that A codes need significantly large amounts of pre-shared secret information. And the issue is how we can make such information available and how we can manage such information. We propose what we called key bank agents for doing that, and we need something like an authority to control that, like in the public key infrastructure. There are more than one possibility to offer such requirement for cryptographic keys, and what we are proposing really is based on quantum key distribution. Why quantum key distribution? Simply because it is an approach that can achieve perfect secrecy based on laws of physics. As far as quantum mechanics is true, quantum key distribution is secure, and there is no way to successfully attack such a system either from classical or quantum physical perspective, as far as quantum mechanics is true. We already have many or several constructions for quantum key distribution networks, but I want to focus that we need to do re-engineering of some protocols, and we in the current information security or internet infrastructure to allow for quantum key distribution and to allow for unconditional secure authentication codes. Here is an example of our some other protocols like IPsec and other wireless security protocols. The main conclusion is that I think it's time to consider a new security services based on unconditional security, not only computational security. And I think the first application that can be considered may be government to government setting, and a next phase can consider e-voting for such application. And last thing I want to say that our work in this direction till this moment is only within our labs. I hope that we can extend our work to some public networks. Thank you very much.
Any questions?
Thank you, Doctor, for the presentation. Very nice. I just have a few points that I'd like to clarify, if possible. You mentioned, for example, quantum encryption, which is not, you cannot look at the packet in transit, but you can look at it when it's received. And you're discussing during your talk unconditional security. So, but what really you're doing is you're only taking care of the technical part of it. What about things such as like social engineering? What about things such as malware, attacking endpoints? You're never, like most penetration testers or hackers or crackers are doing these days, they're never actually attacking the protocol while they are attacking the person using the protocol. So for example, yes, you have a whole bunch of keys and they expire and you renew them and everything, but you're still using a computer. One example of that is Stuxnet. The attack on the Iranian nuclear facility. It was completely offline, but all it took was just a small USB to insert it into a mainframe, and then it did all that damage, and it was completely offline. I mean, you can't get more secure than being completely offline. So what about that? Like, how do you address those issues?
Yes, of course. What you said is completely right. This is an issue that we have to consider all the time, but considering quantum key distribution, as far as we are implementing it in the right way, we are sure that it's not possible to clone the information, because if the information is at the quantum level, there's what we call the non-cloning theorem. It's not possible to make a copy of this information anyway without disrupting the quantum system. So there's a physical law that protects the system in this time. And of course, I have to repeat that as far as quantum mechanics is right.
Thank you. Thank you. All right. Thank you very much.
Thank you.